Hello, welcome to the 10th lecture in ML series. In this lecture has three parts. The first part where we will be discussing first approach to solve parameters of a linear regression, that is the normal equation approach, and the second approach to find parameters of a linear regression, that is gradient descent, in second part, and in third part we will be discussing practical implementation of the gradient descent approach. Okay, so let us quickly recap what we discussed in the previous class. We have formally defined the linear regression problem, where the target function is a linear relationship between the target variable and the features. Here x1, x2, so on, xn are the features and the target variable is y. And there is a linear relationship, that's why we have theta naught plus theta 1 x1 plus theta 2 xn, so on, theta n xn. And the performance measure is the mean squared error, that is the average of the square difference between the predicted and actual values. Now for a given data set, we have to find a theta such that we have j of theta is minimum. Okay, so it can also be solved analytically. That is, you have a function f of x and you want to find f of x is minimum at some x. Then that can be solved by using a calculus properties. That is, you can find f dash x, that means the derivative of f of x, and equate it to 0. Then you can find some x at which that f of x has a minimum or a maximum. Then again you can take f double dash x. Depending on f double dash x, whether it is greater than 0 or less than 0, you can say that f of x has a minimum or a max value. Now by using those properties, first we will be deriving this j of theta is having a minimum at a particular theta. So that is a direct approach. So as there are two parameters and both parameters are independent each other, we will be using partial derivatives. So we take a partial derivatives and then equate it to 0, then we get two equations. Solving those equations, we will get the parameter values. Here when you have for a simple linear regression, we have only one dependent variable and one independent variable. So you have this theta naught plus theta 1 x is the representation of the hypothesis. Then we have the squared error is j of theta naught theta 1 is 1 by 2m sigma theta naught plus theta 1 x I plus minus y of I whole square. Okay, so first you take a derivative with respect to theta naught. So dou j by dou theta naught, and it is in the form of x square. X square is 2x. So and then theta naught has a coefficient 1, so we'll get a 1 here. And similarly dou j by dou theta 1, and theta 1 has a coefficient xi, so we'll get xi. Remaining are 0 because it is independent of theta 1. So we have this. Now we consider the first one, and when you do a simplification, we get sigma I is equal to 1 to m theta naught, so that will be m times theta naught plus theta 1 into sigma I is equal to 1 to n xi, and if you divide m both sides, so you get 1 by m into sigma I is equal to 1 to m xi, that is nothing but a mean value, that is x bar, and similarly y bar. So if we take this side, then we'll get theta naught as y bar minus theta 1 into x bar. This, let us consider this as equation 1. Similarly, dou j by dou theta 1 also equated to 0. That 1 by 2m will cancel. So we have, if you take xi inside, then we'll have theta naught xi, theta 1 xi square. And if you substitute theta naught of equation 1 into equation 2 and then simplify, we'll get theta 1 as this sigma I is equal to 1 to m xi minus x bar into ya minus y bar by sigma I is equal to 1 to m xi minus x bar whole square. And if you substitute this one into equation 1, you can find out theta naught. And by using a linear algebra properties in a matrix form also, we can solve for theta as x theta is equal to y, and theta we can write it as a x transpose x inverse into x transpose y, where every row corresponds to one training example. Every training example has x1, x2, so on xn values and a y1 value. So, and we will be having extra ones here. Those will be coefficients of theta naught. Okay, and so here we have to find an inverse as well as we have to do a matrix multiplication. It is computationally expensive. So let us try to understand this one on one example. So let us recall that example that we had considered in the previous lecture for this regression problem. So we have 4 training examples, and we had given the number of study hours and the respective exam scores. Okay, and then here we are interested in finding a relationship between y and x1. So let us consider we have a linear relationship, then y is theta naught plus theta 1 into x. We have to find the theta naught theta 1 by considering this data set. So we can directly compute theta by using this equation x transpose x inverse into x transpose y. So first we'll consider this x as, so we will be adding ones. These are the theta naught coefficients, these are theta 1 coefficients. So 1, 2 corresponds to the first training example, 1, 4 corresponds to the second training example, 1, 6 third training example, 1, 8 fourth training example, and the respective study hours are your y. So x transpose is this, and then if you do x transpose into x, you will get this square matrix 4, 20, 20, and then we have to take the inverse. If you take inverse, we'll have 1.5 minus 0.25 minus 0.25 0.05, and calculate x transpose into y also. X transpose y, that is 11412468. Then you'll get 310.1690. And if you calculate theta by using that, we'll get 42.5 and 7.0. So that is the equation that we get is 7.0 into x plus 42.5. That's, by using that we can also predict for any number of hours. Like suppose if you want to predict for 5 hours, what is the score? That is 7 into 5 plus 42.5. So 35 plus 42.5. So this is the direct approach for computing the theta naught, theta 1 values. But the difficulty here is it is computationally expensive, because we have to calculate inverse and as well as a matrix multiplication, and sometimes it may not be a singular, inverse does not exist. Oh sorry, sometimes it might be a singular. In that case, inverse does not exist, and for non-convex functions, it's not possible to have a direct solution also. For those, we will be using a gradient descent methods.